Hello there. Welcome to the class of understanding trees. So here is the list of the topics that we will be discussing today. The first thing that we will going to discuss is the linked list, and then after we will move towards trees. I included here linked list because the implementation of trees is somehow similar to the implementation of linked list. That's why we will be first get started with linked list, and then we will be moving to trees. And also, I will be implementing my whole logic and whole code in C++. If you are using some other language for yourself, you can check out different blogs on the internet, and you will be able to understand the implementation details in that language. While the logic behind the implementation is similar in any language. Moving forward to the introduction of linked list. Linked list is nothing but a list of objects. Of course, there may come a doubt in your mind that why we are using linked list to implement list when we have inbuilt data type of arrays and vectors to implement list. The reason behind this is very simple. There are many practical applications of linked list. For example, stacks, queues, and dequeues, which can be implemented very efficiently if we use linked list. But if we use arrays or vectors to implement stack queues or dequeues, it will be memory inefficient and a higher cost of memory will be used. Formal definition of linked list. Linked list is nothing but a connection of nodes, and these nodes are created dynamically in the heap section of memory. As we know, there are four sections of memory available in our PC. The four sections are the heap section, the stack section, the code or text section, and the static section. And different sections have different kind of functionalities in the PC. When we create a linked list, the different nodes we create, those are created in the heap section of the memory, and then those are connected with each other so that we can traverse our list. Here you can see that each node contains two subsections. The first subsection is called the data, and the other subsection is the next subsection. And usually the next subsection, usually, or you can say definitely, the next section will be containing the reference to the next node in the list. So let's have a look at the node that will be created in the heap section of the memory. In the memory block in the heap section that we will be looking at here has two subsections. The first subsection contains the data part. Here we can store the data that we desire to store. For example, let's say we want to store the salary of the employees of a company. Then this data will be integer type. Or if we want to store the names of the different employees that are currently in a company, then this data will be string type. And the second subsection of the node is the address to the next node, so that we can traverse the list. Let's have a look at linked list, how a linked list looks like if we draw it structurally. So we have a variable named head, which points to the head of the linked list. The head variable contains the address of the head node of the linked list. And here you can see the first node, that is the head node, contains the next address as 400, which is the address of the second node in the linked list. Then after, the second node contains the information, the address of the next node, that is the third node, which is 358 here, you can see clearly. And the third node contains the information 250, which is the address of the next node, which is the last node here. And in the final node or in the last node, we set the next pointer to null so that we can identify that, okay, we have reached to the tail of the linked list. Usually, the first node in the linked list is called as head and the last node in the linked list is called as tail. Let's have a look at the application of linked list. The linked list are used to implement stacks, queues, and dequeues. We can use linked list to implement stacks, queues, and dequeues, which will be memory efficient, and also the cost of different operations like pushing or popping out elements will be lesser as compared to the implementation using arrays or vectors. The second application of linked list comes in the stack section of memory. The stack section of memory in our PC uses linked list for different recursive and multiple function calls. Moving forward, let's compare arrays and linked list. The cost of accessing an element in an array is of constant time. It is of big O of 1. While in linked list, to access an element, we need to traverse the linked list, and hence in average case, the time complexity will be big O of n. Also, the memory requirement in the array will be of fixed size. Hence, if we are having the list or the number of data available at us lesser than the defined size of the array, then there will be a lot of unused space remain in the array. While if we use linked list, there will be less amount of data. There will be no amount of unused memory that will be wasted. The next cost comparison basis will be the cost of inserting an element. In array, if we want to insert an element at the beginning, the cost of this operation will be big O of n, while in linked list it will be big O of n. If in the end we want to insert an array, then the cost of operation will be big O of 1, while in the linked list it will be big O of n. At the ith position, in the both of the arrays and the linked list, the cost of inserting the element will be big O of n. And of course, the last comparison basis is the ease of use. The ease of use will be more better in array than as compared to linked list, because if we want to access something, we can write a of that ith element, and we can access the ith element in the array. While to access that element in the linked list, we need to traverse to the ith element. That's why the ease of use of arrays will be more easier than linked list. So now we will be implementing linked list. Basically, linked list are of two types: the singly linked list and the doubly linked list. Singly linked list are those which contains only the information of the next node, while the doubly linked list, in the doubly linked list, the node contains the information of the previous node as well as the next node, so that we can at any time from any node traverse forward as well as backward. So let's do some VS Code. Okay, let's start implementing linked list. As you can see, I have opened VS Code in my laptop, and before implementing the insertion of the elements in the linked list, I will be explaining you the main logic here. Here, I defined a variable named n, which will be storing the size of the linked list that we desire to create, while I can add or remove nodes later in the program. So I will be first taking the input n, and then I will be traversing, or you can say I will be iterating, or I will be counting from 0 to n minus 1, so that n elements can be taken. Here I defined two variables, int x and n. The x will be the number, the element that we will be desiring to insert, and n will be the position at which we want to insert this element. So now let's move to the logic of this insert. Before moving to the insert function, let's have a look at this struct part. I defined struct node here. Struct is a keyword that is used to define user-defined data types in C++. In this struct node, I have two different sections. The first section, or the first part, says int data, that is to store the integer data type of this node, and the second part contains node star next, which stores the information or the pointer to the next node. I defined here node star head, which will be globally representing my head, the pointer to my head. Okay, let's move to this insert part. In this insert function, I firstly catch the parameters x and n, and then after I defined a temp variable, which is nothing but dynamically created heap section. And in this temp heap section, I defined its data part to be x and set its next pointer to null if n equals to 1. That is, if we are trying to insert the element at the first position, then we will be simply setting the next variable of the temp to the head and head to the temp, so that the new head can be set to the temp, and the temp contains the next as the previous head. In the else part, we will be firstly iterating to the n minus 1th node, and then after we will be resetting the links so that we can put our temp section in between n minus 1 and nth node to create the temp as the nth node. So let's start trees. Introduction to trees. Whenever we need to store some data, how we decide which data structure to be used. There are four factors on which we should decide the data structure that needs to be used in order to store the data. The first one is the what needs to be stored. The second one, cost of operations, the different operations that we perform on the data and their associated cost. The third one is the memory usage, and the fourth one is the ease of implementation. With these four factors, we will be deciding which data structures needs to be used in order to store the data that we have at the time of application. Tree is an efficient way of storing and organizing data that is naturally hierarchical. Collection of entities called nodes linked together in hierarchical fashion. Here is the diagram of a tree. The circle represents the nodes and the arrows represents the edge. The node 1 is called the root, or the node which does not have any parent is the root node. Children. Any node which has some parent is called the children node. Parent node. Any node which has some child is called the parent node. Here 2, 3, 1, 4, 5, 2, 3, 1 are parent node. 5, 6 are also parent node. 7 and 8 are also parent node. Siblings. Two nodes are said to be sibling if they have same parent. Leaf. A node with zero child is a leaf node. In this given diagram or in this given tree, node 4, node 9, node 10, node 11, node 8 are the leaf nodes. Tree is nothing but a recursive data structure. Something which reduces itself in self-similar manner is called a recursive data structure. A tree with n nodes have n minus 1 edges. Okay, now let's us talk about depth and height of a node. The depth of a node is the number of edges in path from the root to the next to the node x. Height of the node x is the number of edges from node x to some leaf node, and this number of edges should be maximized. The more formal definition is the number of edges in the longest path from x to a leaf. Height of tree is the height of the root node. In this video, we will be specifically talking about binary trees. Binary trees are the trees in which each node can have at most two children. Here, this diagram depicts a binary tree. Each node have at most two children. You can see very clearly. This is another diagram that is used to show a tree. Here, a tree node is depicted by three blocks. The middle block represents the data. The left and right block represents the left child, and the right child. The left block contains the address to the left child, and the right block contains the address to the right child. A tree, when implemented in C++, is represented or is depicted in this way, can be created in this way. A node will be defined by three parameters. The first parameter is the data, the second and the third parameter are the left child and the right child pointers. Application of trees. To store naturally hierarchical data, For example, in file system, we will be using trees. To organize data for quick search, insert and deletion, binary search trees are used. Try, which is used to implement dictionary or store words, is nothing but a special tree. Network routing algorithms also uses tree. Okay, let's start binary tree. Strict or proper binary tree. Trees in which each node can have either 2 or 0 children is called a proper binary tree. That is, none of the nodes can have single children. Complete binary tree. All levels except possibly the last are completely filled, and all nodes in the last are as far as left as possible. This figure here, this figure here shows a complete binary tree. Each node have each of the levels are filled, and the last level here have 3 nodes which are in the left as possible. Maximum depth of a tree is also equal to the height of the tree. Maximum number of nodes at level I is equal to 2 to the power I. The root is called the level 0. Then after, the next childs are said to be at level 1, and so on. A perfect binary tree. If all levels are completely filled, a perfect binary tree is constructed. This tree here is a perfect binary tree. Each of the node has exact 2 children, and all of the levels are completely filled. Maximum number of nodes in a binary tree with height h is equals to. We can see the first level has 2 raised to the power 0 number of nodes. The second level has 2 raised to the power 1, so on and so on. In this way, we can construct a formula 2 raised to the power 0 plus 2 raised to the power 1 plus 2 raised to the power 2 and so on up to 2 raised to the power h, and it will give us 2 raised to the power h plus 1 minus 1. That is, 2 raised to the power the number of levels minus 1 is the maximum number of nodes that a binary tree with a height h can have. Also, rearranging the terms, we can see that the height of a binary tree is nothing but log of n plus 1 base 2 minus 1. Height of a perfect binary tree with n nodes is this. Height of a complete binary tree can be found out by log n base 2 and its floor value. The cost of the various operations on a binary tree will be directly proportional to the height of the tree. That is, the time taken for various operations on binary tree is directly proportional to the O of h, where h is the height of the tree. H we will try to minimize. We will try to create or to keep the binary tree balanced. In this way, the height will be minimized and the time of various operation will be reduced. A tree with n nodes, the minimum height possible will be the log n base 2 floor, while the maximum height possible will be the n minus 1. This tree is called a sparse tree. We can see a tree which is represented here, which is more of a linear tree, and this tree have a height of n minus 1, and the cost of various operations on this sparse tree will be higher. Now, balanced binary tree. A tree in which the difference between the height of the left subtree and the right subtree is not more than k. In most of the cases, k is considered to be 1. Those trees are called balanced binary trees. Height. Number of edges in longest path from root to a leaf. Height of an empty tree is minus 1. Height of a tree with one node is 0. Height difference equals to height of the left subtree and the height of the right subtree minus height of the right subtree. And in a balanced binary tree, this difference is always less than or equal to k for every possible node. Now we will be implementing trees. There are two ways to implement trees. The first way is the dynamically created nodes wedge. In this way, we create nodes dynamically in the heap section, and each node contains the pointer to the left node and the right node. The second way in which we can implement a tree is the array way. Using an array, we can also represent a tree. For node at index I, index of the left child will be 2i plus 1 and the index of the right child will be 2i plus 2. Basically, if we want the child of 0, its left child can be found at 1 and right child can be found at 2. That is, 2 has left child as 4 and right child as 2. Similarly, for the left and right child of 2, the left child can be found at 5 and the right child can be found at 6. The left child of this node 2 will be 7 and right child of this node 2 will be 9. We will be learning binary search tree from now onwards. A binary search tree is a tree in which all the childs that are left to a node are lesser and all the childs that are right to a node will be greater. Which data structure we should use for modifiable data set? Of course, we will be using binary search tree in which there are various modification operations involved, because search, insert and remove operations are O of log n in binary search tree, and we will be looking why these operations are O of log n in binary search tree in further slides. For n records, log n base 2 comparisons will be needed for searching something, inserting something and removing something, and hence only 31 comparisons will be needed, and this way the time complexity will be reduced a lot and efficiency get higher. Let us define binary search tree more formally. A binary search tree is a binary tree in which for each node, say its value is v, value of all nodes in the left subtree is lesser or equal to v, and values of all the nodes in right subtree is greater. Here, this pictorial representation says, let's say we have a node or the root node and its value is v. All the nodes have values in the left subtree lesser or equal to v and the right subtree greater than v. Here is an example of binary search tree. Here we can say node 15 has left subtree as 10, 8, 12. All the nodes in the left subtree of 15 has values lesser than 15 and the values of the nodes in the right subtree are greater than 15. Hence, this is an valid BST, valid binary search tree. While this tree is not a valid BST because here we can say node 16, which lies to the left of the 15, has value greater than 15. While this is violating the rules or the definition of a BST. Hence, it is not a BST, not a binary search tree. We know in binary search, we need log n base 2 steps to search something. Similarly, to search something in a binary search tree, we will be using only log n base 2 steps if the binary search tree is balanced. Because here we can see, let's say we want to find 12. At a time, at a step, we can discard half at a time, we can discard half portion of the subtree. Because let's say we want to find 12 in this tree. 12 is compared with 15 and it is less than 15. Hence, we will be surely know that 12 can lie either to the left of the 15 or it will not lie in the tree. Hence, we will be moving towards the left of the tree. We can clearly see here the right portion is neglected and hence the search space is reduced by half. Here again we arrive at 10 node 10 and we know we want to look for 12. Then the 12 can lie either to the right of the tree or doesn't lie in the tree. Hence we will be moving towards right. And now we have arrived at 12 and we know that 12 is been arrived and hence we found the node. And clearly we can see here at each step half of the portion of the tree is discarded. Hence only log n base 2 steps are needed to search something in the binary search tree. Also, if the binary search tree is not balanced, like in this example, this tree is a sparse tree and also a valid binary search tree because all the nodes in the left of a node have values lesser than the node. You can see clearly here. And in this tree, if we want to search something, we will be having O of n minus 1 steps, O of n complexity of searching something. Hence, to arrive at a time complexity of log n base 2, we need to have a balanced binary search tree. Let's talk about insertion of a node in binary. Okay, let's start the insertion logic from here. If we want to insert a node in a binary search tree, that will lead us to a time complexity of O of log n, which we can see here. Here we have a binary search tree and we want to insert 19 to this binary search tree. Clearly 19 is greater than 15, hence it needs to be inserted in the right subtree. We will move towards the right and now we will be arriving at node 20. Now 19 is lesser than 20, hence we will be moving to left subtree of this 20. Now we arrived at 17 and there is no further child to, if there is no further child to 17, we will surely say that 19 needs to be inserted to the right of this 17. Now, here is the two steps, here is the two key points that needs to be keep in mind in order to insert a node in a binary search tree. If we want to insert a value that is lesser than or equal to a given node, then either we have a left child or there is a no left child. If there is no left child, we will insert the value right there, or else we will go in the left of the tree. If the value we want to insert is greater than the current node, then if there is no child, if there is no right child, we will insert it there, or if there is a right child, we will go in the right subtree and we will insert the node in the right subtree. If you understand these 2 points of insertion, the implementation of insertion will be easier for you. Here, in the insertion of the node, BST star root represents the root of the tree that we are considering, and int data represents the value that needs to be inserted in the BST. If root is null, then we had arrived at the place where this data needs to be inserted, and we will be calling this function get new node. Get new node will be creating a new node and setting its value to data and returning the address to it, and we will be catching it into the root, and we will be returning the root here. Or if the root is not null, then the value associated with the root, if it is lesser than the data that needs to be inserted, clearly the data needs to be inserted, then the data needs to be inserted in the right, then the data needs to be inserted in the right subtree, and we will be calling root.write equals to insert root.write comma data. Or if the data associated with the root is greater than the data that needs to be inserted, then the data needs to be inserted in the left subtree, and we will be calling root.left equals to insert root.left. Binary search tree. In binary search tree, let's say we have given with the root of the binary search tree and the data that needs to be searched in the tree. If root is null, then clearly we had not found the data and we will be returning false. Else if root.data is equals to data, then we will return true. Or if the data that needs to be searched is greater, then we will look for the data in the right subtree and we will call the recursive function search with the root as root.write and the data as data. Or if the data is smaller than the value present in the root, then this data can be found in the left subtree, and we will be calling the recursive function search with root as root.left and data as data.